Okay, equilibrium reactions and how they are affected by LeChateliers Principle, or in other words, I know what you did last recess. So we're going to take this whole idea of equilibrium reactions. Think of it in terms of something that hopefully all of you have done at some point in your life in a very crude model of what we're talking about with a reaction, because clearly we can't represent the atoms on the molecular scale, but we're going to put it into terms that hopefully you'll be able to think of and use and make sense of what's going on in a world that you can't see. So equilibrium, just as a little reminder, an equilibrium reaction is where the reactants form the products at the same rate that the products form the reactants. The two most common occurrences are when we have gases in reactions or when we have chemicals that dissociate into water. And if you remember that, that means they are aqueous. So those are our two most common places where we're going to see this type of reaction. So equilibrium is like a teeter-totter or seesaw, and this is again where I'm hoping that maybe you'll have some knowledge of this in your head from when you were little playing on a teeter-totter, going up and down and thinking of now on the molecular terms what's happening in a reaction. So we have elementary school, we've got Katie and Anya here, and they are going to be on our teeter-totter. And they are nice and happy on their teeter-totter. One goes up, one goes down, one goes up, one goes down. Overall, they have a net spot right in the middle, and that's why it's listed right in the center there, nice horizontal line. But what happens when the teeter-totter is out of balance? So somebody else comes along, like Ethan. He's the funny guy, so he is getting onto the seesaw on Katie's side, and now, no matter how hard Anya tries, she is not able to get the seesaw to go back down and up and down and up like the equilibrium that they had created in the first place. So how can all three of these kids play on the teeter-totter and still be happy? Well, we changed the system. So we put a stress on the system. Ethan was a stress on our system. We want it to go back to normal so everybody can play. So what they do is they figure out a way to get back to equilibrium. So Katie and Anya are on one side and Ethan's on the other, and they're all having a great time now because their net overall difference is that horizontal line again. And we've got each of them going up and down in that equilibrium. If one goes up, the other one has to go up to counteract that. Now, what you're going to probably be doing during the tests, and I highly recommend this, is use a pencil, the pencil that you're writing on the test, to think about nice horizontal line being our equilibrium. And then you're putting stresses on it, and we're going to keep thinking of the teeter-totter and what has to happen to get it back to horizontal. So everybody's happy here. Now, that's not exactly how the chemical equilibrium works, but it's a good way for us to start thinking about it. And it's all called LeChateliers Principle. And it's where a system at equilibrium is disturbed or stressed, the system is going to correct itself to restore equilibrium. So we think of this in two steps. We think something external puts a stress on the system. So I often think I am doing something to stress it out. And then the system does something internally without my help to get itself back to equilibrium. So what does that mean? Well, an equilibrium reaction is similar to our teeter-totter. When the kids were given a new set of conditions, they found a way to make it work. And when a reaction is given a new set of conditions, it's going to find a way to make it work too. So what does that mean? The teeter-totter was initially at equilibrium, that was our Katie and our Anya, and then the equilibrium was disturbed. Ethan came in and stressed out the system. But the system fixed itself. The kids found a new way or new equilibrium, even though it's different from the original equilibrium. And that's where all three were playing nicely on the teeter-totter. So let's look at some chemistry. We have some iron ions and some thiocyanate ions in a reaction. Now, the iron is bonded to something else. Maybe it's a chlorine. It's dissociated in water, though, and that chlorine is not part of this equilibrium, so the chlorine's just floating around in the solution. And then the thiocyanate, that's bonded to some cation, but that cation is just floating around because it's an aqueous solution as well. And I don't need to write it because it's not involved in the reaction. And that's in equilibrium with a new ion that's formed. So this is funny. This looks like it should be a compound, but we see that charge right there. We have another ion forming. So this is iron thiocyanate. It's bonded to some other anion to get it to equal out in the net charge, but it's again ions just floating around in the solution. And those are in equilibrium, and what we'll see, and once we talk about redox reactions, this will make sense, the color of the solution is going to change because we have the different charges of the irons, and different charges of irons have different colors. So let's put a stress on this system. So we are going to add some iron 3 chloride solution to the solution. So I'm adding more of the Fe3+. So that's my stress that I'm doing. I'm adding more to this side. So I'm weighing down this side. Let's look at some teeter-totters. So I've got nice teeter-totters at equilibrium. This is my reactant side. This is my product side with the iron thiocyanate. This is my iron ion plus my thiocyanate ion. And now what I'm going to do is I'm going to add more, let's see, add more of the iron solution, or the ions, into solution by adding more iron chloride. And so I've put it out of balance. This is what I have done to it. Now the solution has to get back to equilibrium. So what has to happen is I have to start forming some of the products to go back to equilibrium. So I made it go down on the left. It's going to have to shift to the right. I'm going to have to add more to get this to go down to get back to equilibrium. So if the iron ion is increased, I'm increasing the concentration of the iron. That's what I have done to it. What the reaction will start doing is creating more of the products. The forward reaction, or going to the right, is going to increase to offset that change. So I stressed it out by making this part heavier. So it has to form more of my products to get it to even out again. If I decrease the concentration, well, you're probably thinking, how on earth am I going to do that? You're actually going to do that by introducing something new into the system. So let's say I add something that's going to bond to the iron 3+, thereby decreasing its concentration. So let's look back at our pictures. And what I have done now, there we go. I added a new compound that bonded to one of my oranges, and so it took it out. I removed some of the iron 3+ ions. So what's going to have to happen is I'm going to have to shift towards the reactants. I'm going to have to form more of those reactants to end up to get this to balance. So I'm going to shift to the reactant side, or shift to the left. And again, this is where you can be using your pencil, going back and forth and seeing what's going on. So to go back to the equilibrium, the forward reaction would decrease and the reverse reaction would increase. Okay. If I have a gaseous system, I said that there's two main types of systems, either aqueous ones or gaseous ones, or ones of gases. If I change the pressure, that's going to have an effect on my equilibrium, because that's putting a stress on it or a strain on it. So if I increase the pressure, we're going to have a shift to the side with the least moles of gas. So this is where our balanced equation comes in handy. I know my moles of gas by looking at the coefficients. So it'll go to the side, either reactants or products, that has the least number of moles. So I would add them up. If I decrease the pressure, it's going to go the other way. It's going to shift to the side with the most moles. Now, it's not always going to be towards the products or the reactants. It depends on which equation or reaction I have. So let's look at one good equation. I've got hydrogen gas and oxygen gas in equilibrium with water. and I want to see, let's say, increasing pressure. So I'm going to increase the pressure. Well, I have to look at the total number of moles on each. So I have 2 plus 1. I have 3 moles on my reactant side. I have 2 moles on my product side. So if I'm increasing the pressure, that's the stress that I'm doing. What the system does to get back to normal is it shifts to the side with the least moles, which on this side happens to be the product, so it would shift to the left. If I was decreasing the pressure, it would shift to the side with the 3 moles, so the reactant side. Now if I add a catalyst, it's not actually going to affect the equilibrium. We know it's going to affect the rate, but it's going to reduce the activation energy in both directions, therefore making both the forward and the reverse reaction speed up. And here's kind of our tricky one, temperature. If I increase or decrease the temperature, what's going to happen? Well, I have to think to 2 units ago, topic 5, and energy. So I have to remember what's going on with energy changes in a reaction. If I have a negative delta H, that means I'm releasing energy, so I'm exothermic. Or another way I could write this is with plus heat as one of my products. And then if I had a positive delta H value, I'm going to be endothermic. I'm taking energy into the system to make the reaction occur, and heat can be written as a reactant. The reverse reaction is whatever opposite sign of my forward reaction, but it's the same magnitude. So if it's going up, if it's releasing 1 joule of energy in the forward reaction, it would have to take 1 joule of energy in the reverse reaction to occur. So if the temperature of the system is increased, both the forward and reverse reactions are going to increase, but at differing rates. The reaction is going to shift to the more endothermic part of the reaction. So it's going to shift to the side that would have a positive delta H. And that's because it has a higher activation energy to overcome. And since it has that higher energy activation to overcome, it's going to be more easy to do that since the temperature is increased. Now, if the temperature of the system is decreased, the reaction is going to shift to the more exothermic part of the reaction. That's because I have a lower activation energy to overcome, so it's easier for it to go towards the exothermic part of the reaction. Now we're thinking back to the Haber process that was introduced yesterday. We said that the reaction was nitrogen and hydrogen gases reacting to form an equilibrium reaction with ammonia. In an ideal world, the pressure would be large and the temperature would be cool, and that's because of LeChateliers. So if we look at this, thinking of pressures, I want to, in industry, form as much of my product as possible. So I want to get as much NH3 out as possible. So I have 1 plus 3, that's 4 moles of gases on my reactant side, but only 2 moles of gases on my product side. And I said pressure is going to be large, so I'm going to increase the pressure. That's the stress that I'm putting on it. So it has to shift to the side with the least number of moles, creating more of my product, the NH3. Now this reaction, it doesn't tell you here which way is exothermic and which way is endothermic, but we can take a look at the information. If I cool the temperature, if I make it colder, decrease the temperature, what would be happening? Unfortunately, in industry, high pressures are expensive and they're dangerous, and we want to mitigate as many dangers as possible in industry because we don't want our employees to die. We also have trouble with low temperatures because it makes the reaction slow down. So even though it would form more of my ammonia, it's going to take a really long time to do that, and I don't have a lot of time to waste when it comes to industry. I want to get my product out to the people that are going to buy it. This is a cute video. I'll post it on Schoology, talking a little bit more about the Haber process, and you can watch that in your own time.